In part one of the discussion about heat, we'll focus on talking about temperature and internal energy. So some of the important concepts that we're going to revisit will be kinetic energy, which of course is energy due to motion, and also potential energy, which is energy due to position, or specifically, energy due to interactions between objects. So we've talked about gravitational potential energy in the past, but there are also other forms of potential energy like elastic potential energy due to objects being sort of connected by a spring or something similar to that. So the first topic that we're going to sort of focus on is something called thermal energy, which is often also called internal energy. And so we have a picture here, and we could ask the question, what is the obvious differences between these two pictures? And so the picture here on the left is just a glass of ice water, and then the picture on the right is supposed to be basically water on a stove, which is boiling. So what are the obvious differences between these? Well, I think the first thing that comes to mind would be temperature, right? So they obviously are at different temperatures. One water is boiling, one is ice water. So it turns out that all substances are made up of atoms and molecules, and we know this. And those molecules actually carry energy. So I have a picture over here on the right, which is supposed to represent molecules of a substance. This is most likely a gas, right? Because the molecules are not tightly bound together. And some of the things that you'll see, of course, is that the molecules are in motion, right? They're moving around all over the place, so they do have kinetic energy. But not only do they have kinetic energy, but they're also molecules, and they're like connected together. And sometimes you can see that they're actually vibrating from that connection, like that one right there was just vibrating right there. And that's because they have what's called potential energy associated with them as well, which is sort of holding them in place. And so the combination of the kinetic energy of these molecules and the potential energy of the molecules is called the system's thermal energy. And so if we had a substance that was in a container and it's not in motion, we could still say that the molecules inside that container, just like the ice water and the boiling water, have kinetic energy and potential energy, and therefore they have this thermal energy or internal energy associated with them as they're just sitting there. So now if we went back and we asked the same question again, like what are the obvious differences between these? The ice water here, the molecules would not have as much kinetic energy. The material is at a lower temperature, and obviously here the boiling water is at a higher temperature, but not only is there something related to their temperature difference, lower temperature and higher temperature, but this ice water actually has less thermal energy, and the boiling water has more thermal energy or more internal energy. And we're going to talk about, what is this internal energy and what is it related to, but the motion of those molecules of the substance depend on the temperature. So the ice water molecules, even though these are both made of water, and even if they both had the same amount of water in them, the molecules on average inside the ice water are not moving as fast as the molecules in the boiling water. And so if the thermal energy is related to the sum of like all the kinetic energy and potential energy that's going on inside with these molecules, then the ice water would have less thermal energy because those molecules are not moving as fast as in the boiling water. So that's one of the obvious differences between those two things. Temperature difference, but also there's different amounts of thermal energy. So it turns out that the thermal energy depends on the temperature of the substance. So the higher the temperature of the object or the system, the higher the thermal energy is. And that's related, again, temperature is going to be related to how those molecules move. But thermal energy also depends on the amount of the substance that you have. So if you have more of a substance, then you have more thermal energy. So the amount of a substance is the number of these atoms or molecules that make up the substance. So we'll sort of elaborate on that a little bit more. So if we go back to the boiling water example, if you had 2 gallons of boiling water, it has twice as much thermal energy as 1 gallon of boiling water. And so even though boiling water in both cases is the same temperature, right? Water boils at 100 degrees Celsius. So both of these containers would have the same exact temperature. There's a different amount of material in 2 gallons of water, right? There's twice as much mass of boiling water, twice as many atoms or molecules in 2 gallons of boiling water compared to 1 gallon, and therefore there's twice as much thermal energy. So when we think about internal energy or thermal energy, they both are basically the same thing. You have to remember that it depends on temperature, but also depends on how much of the actual substance that you have. So we could think about the fact that there is a difference between thermal energy and temperature. And so this is kind of a weird example, but it does kind of make sense, I think, once we talk about it. So we've got this boiling water here. And suppose you were to spill a cup of boiling water on your hand. So maybe you were to making a cup of tea, and you poured this boiling water into your cup, but then your cup tipped over and it spilled on your hand. Obviously, that boiling water would burn your hand, and it would burn your hair. It could burn your hand pretty severely. But how is that different than if you were boiling the water? And I've done this before where I'm making pasta or something. The water is boiling, and you go to put something in the water, and a droplet of water comes out of the pot and lands on your hand. That small drop of boiling water lands on your hand, but it doesn't really burn you. And so even though the water in both of those cases is at the same temperature, it has a different impact on your hand or your skin. And so the thermal energy is actually what's transferred to your skin, and it's what burns you, not so much the temperature. So the small drop has very little thermal energy. It has a very small amount of mass for a very small number of molecules, so a very small amount of thermal energy, and that's because the drop is small, right? So small amount of thermal energy is not going to transfer as much energy to your hand to cause that burn to occur. So there is a difference between temperature and thermal energy. The thermal energy depends on the temperature, higher temperature, more thermal energy, but it also depends, the thermal energy also depends on how much of the substance that you actually have. So we've mentioned temperature a few times, but we haven't been very specific on what that actually is. But I think it's something that we know pretty early on in our academic lives, even in elementary and middle school. But temperature is basically the quantity that measures how warm or cold an object is. So hot and cold are relative terms. One person might think that it's warm outside, another one might say that it's cold, or another person might say it's hot. So when you talk about temperature, in some ways, using the term hot and cold is very relative. But if we say temperature, we're actually measuring something. We're being very specific, and we're measuring how hot or how cold something is. And more specifically, what temperature measures is if we measure the temperature of a substance, we're measuring the average kinetic energy of the molecules that make up that object. So we know that molecules move around inside of a substance. And we're going to talk a little bit more about that. But if we had that gas model that I showed the picture of, those gas molecules are moving around, and we could calculate their average kinetic energy. So we could look at each individual molecule, we could figure out the kinetic energy, and if we averaged those kinetic energies together, that would tell us the temperature. Not all of the molecules are moving at the same speed, right? So they don't all have the same kinetic energy. So temperature is an average value for those kinetic energies. And we can't obviously add up all their kinetic energies, but it just gives us an idea of, what temperature is actually measuring. And it doesn't matter how much of the substance that we have. So if we had a big pot of boiling water or a small pot of boiling water, they still have the same temperature, 100 degrees Celsius. And so if we added up all the kinetic energies in both of those pots, but then took the average would still be the same. All right, so let's look at an insight question. This is kind of a weird way to say it, but which has more temperature? Probably a better way to say it is which is at a higher temperature, a red hot tack, I think I spelled tack wrong, or a cool lake. In terms of temperature, the red hot tack, something is red hot, it means it's very warm, right, is at a higher temperature as compared to the cool lake. So in terms of temperature, certainly that tack is hotter. Which has more thermal energy? And this one is harder because although the red hot tack, so a tack, just a little thumbtack, the tack, a metal thumbtack, so the tack is very small compared to the large lake. It's at a higher temperature, but it has a very, very small amount of mass. So it turns out that the cool lake actually has a much greater mass, and even though it's at a lower temperature, it has more thermal energy due to its large number of molecules that it has. Because remember, thermal energy depends not only on temperature, but how much of the substance that you actually have. So in terms of temperature and looking at the temperature of different phases of the material, temperature is, of course, proportional to the average kinetic energy of these particles. So in a gas, it is it's the average of how fast those gas particles are bouncing to and fro. So if we could, again, they're not all moving at the same speed, but if we could somehow measure all of their kinetic energies and then average them together, that would give us a relationship to what the temperature is. In a liquid, it's how fast the particles slide and jiggle past one another. So in a liquid, the molecules are more tightly bound together, but they do still move around. And then in a solid, it's how fast the particles move as they vibrate and jiggle. So in a solid, the molecules are more tightly bound together. And even though they're tightly bound, they can still move a little bit, and they do have kinetic energy when there is some temperature associated with them. And of course, we can't see this looking at a solid object, but inside, those molecules are actually vibrating a little bit due to the fact that they are at a particular temperature. And if we could measure the average kinetic energy of those vibrating molecules, that would tell us what the temperature is. So as we measure temperature, we use thermometers, and we rely on the fact that objects expand when heated and contract when cooled. And of course, I also have here, there are exceptions to this rule, and we're going to talk about the exceptions to this rule. But in general, you can take a liquid and put it into a thermometer casing, and what happens is that when you change the temperature of the liquid, that liquid expands, and there's a scale on the thermometer, and based on how much the liquid expands, we can tell what the temperature is and how the temperature changes. So that's a liquid thermometer. But there's also electronic thermometers, and there's different things. But they all rely on the fact, in general, I guess there's a lot of newer thermometers now, but the older thermometers rely on the fact that objects expand when heated and contract when cooled, or they rely on the fact that as the temperature changes, some property of the material also changes. So in the beginning stages of thermometers, we used a property of water, and you have to pick references for water, like the freezing and boiling point of water, and you would mark those on your scale, and that would allow you to then determine the temperature. So, okay, so how would we create a temperature scale? So basically, here is a liquid thermometer, and there is some liquid inside of that thermometer. And what we would do is we would have the freezing point of water, which is 0 degrees Celsius, and we would have our liquid in our thermometer, and we would put our thermometer at the freezing point of water, and we would put a mark on the thermometer. I'm just going to put a line right here, right? It would be right here. And then what we would do is we would heat the water up until it boils, and the water boils at 100 degrees Celsius. So I would then put another mark on my thermometer up here. So I would have a mark for the freezing point, I would have a mark for the boiling point. And then to create our temperature scale, what you would have to do is between those 2 points, those reference points, you would have to put divisions on the scale. And so for the Celsius scale, we have defined the freezing point of water is 0 degrees Celsius and the boiling point is 100 degrees Celsius. So there's the 0, there's 100, and then to create that scale, you just have to put equal divisions between those 2 points on the scale, right? So I would have to make 100 divisions, and of course it's not broken down by 100 here, but I'd have to put equal divisions between 0 and 100 on the Celsius scale, and that would define my Celsius range. We also have something called Fahrenheit, and the Fahrenheit scale uses the freezing point of water to be 32 and the boiling point to be 212. So you would put 32 right here, which is the freezing point, 212, which is the boiling point. The divisions between 32 and 212, the difference between that is 180, between here and here. And so you'd have to put 180 divisions on the scale to represent the Fahrenheit scale. And so I always like to tell students the scales are somewhat arbitrary. So I could create the the physics professor scale, for example. And if I did that, I just have to pick the freezing point of water and I have to give it a number. I could say it's going to be 100. And then I could say that the boiling point is going to be 300, and then I just put my divisions on my scale and I have a new temperature scale. So in some ways, these temperature scales are somewhat arbitrary. So, but there is a relationship between them. And so here we have on the axis the Fahrenheit scale, and we have the Celsius scale, and it's a linear relationship between those two. So at 0 degrees Celsius, the temperature is 32 Fahrenheit, and at 100 degrees Celsius, the temperature is 212 Fahrenheit, and so we could find the slope of this line, which would be the rise over the run. The run along here is 100. The rise is 212 minus 32, which is 180. So I've got 180 over 100. The slope of that line is 9/5. The y-axis is the temperature scale in Fahrenheit. The x-axis is the temperature scale in Celsius. So if I use my equation y equals mx plus b, I get that the y scale, which is the temperature in Fahrenheit, is the slope, which is 9/5 temperature in Celsius, and then the intercept point on the y-axis is 32. So I can convert between Celsius and Fahrenheit using this expression here that tells us how those two scales are related to one another. So when we think about these temperature scales, is it possible to have negative temperatures? And I think that everybody would answer that question as yes. Certainly we talk about the temperature being below 0 outside, especially in very cool regions. So the answer is yes, but the answer does depend on which temperature scale we're talking about. So Celsius and Fahrenheit temperature scales have negative temperatures. But maybe like if I created my own temperature scale, like the physics professor scale, that maybe I could create something that doesn't have negative temperatures, and we're going to get to an example of that. But the answer to that in general is yes. For Celsius and Fahrenheit, we can have negative temperatures. Is there a limit on how low the temperature can be? The answer to that is also yes. The temperature is a measure of the average kinetic energy of the molecules that make up the substance. So the molecules are moving. They can slow down. Eventually, if the molecules stop moving altogether, that means that the temperature is at its lowest possible value. It can't get any lower. We can't have negative kinetic energy. So there is a lowest possible temperature, and it's called absolute zero. And that's when the kinetic energy becomes zero. I accidentally clicked on this one. Is there a limit on how high the temperature can be? And the answer to that is there is no upper limit. There's nothing that says the temperature can't be extremely, extremely high. There's not like a cutoff for how high the temperature can be. So how do we know that there is actually an absolute zero, a lowest possible temperature? And how do we measure that? Because we can't actually cool something down. Well, at least years ago, we couldn't cool things down to be so cold that we're even close to the absolute value. So what we can do is we can use something called a constant volume gas thermometer. And what happens is that you put a gas inside of like a bath or a reservoir, a heat reservoir in here. And what happens is that as you change the temperature of the gas that's in here, it changes the pressure. And what we know about fluid pressure is that we can measure the pressure, whatever the pressure is. So here's my gas, right? My gas comes up into this container, and then I have this U-shaped container which is filled with a fluid. This is an incompressible fluid, so whatever the pressure is at the very top of this U-shape on the left, that must be the pressure of my gas. And I can measure the pressure of my gas by going over to this other side and measure the pressure below the surface of the tube that's opened over here. And I know that with pressure with depth, if I measure this height of this column of this fluid, and I know what the fluid is made of, I can measure the pressure. So I have a way of measuring the pressure of this gas. And so I take the gas, I keep the gas constant, has a constant volume inside here. And what I do is I cool it down. And as I cool this down, the gas pressure decreases. And it keeps decreasing and decreasing. So the pressure of the gas will get lower and lower and lower. And it turns out that I can put different gases into my constant volume gas thermometer. So I have gas 1, gas 2, and gas 3. And this shows what happens as I decrease the temperature. I have pressure versus temperature. As the temperature decreases, the pressure also decreases, right? So, or the other way around, as the temperature increases, the pressure increases. Temperature increases, pressure increases, and so on. But if I cool this down, right, the pressure keeps decreasing. These have different slopes, but one of the things that we could do is as we cool the gases down, we can only cool them to a certain amount. But then we can extrapolate, which means that we would take the line that we have for gas 1 and we would continue it down to see where it hits. And I would do the same thing for gas 2 and gas 3, and what I find is that all of those lines hit a certain point here, which is where the pressure of that gas would be 0. Pressure is also something that has to be a positive quantity, so it can't be negative. So this is the lowest possible pressure of that gas at the lowest possible temperature. And one of the things that you should notice is that lowest possible temperature is negative 273.15, and this is on the Celsius scale. So absolute zero occurs at a temperature of negative 273 degrees Celsius. So in order to have a more scientific scale that actually represents temperature as it relates to the internal energy or the thermal energy of a system, we define something called the Kelvin scale. And the Kelvin scale is actually a more scientific scale because on the Kelvin scale, negative temperatures are not possible. And the actual temperature on the Kelvin scale is directly proportional to the thermal energy or the internal energy of the system. So if we read 0 on the Kelvin scale, we are at the lowest possible temperature, which means that the kinetic energy, the average kinetic energy of those molecules is 0. So it's related more to what's going on with the molecules as they are moving in the system. So The lowest possible temperature is 0 Kelvin, which is equivalent to negative 273.15 degrees Celsius. Again, lowest possible temperature. Kelvin cannot be 0. At 0 Kelvin, the molecules are no longer moving. Their average kinetic energy is 0. It turns out that the divisions on the Kelvin scale are exactly identical to the Celsius scale. So if I take a change in temperature on the Celsius scale, I will get exactly the same change in temperature on the Kelvin scale. So if I want to calculate the Kelvin temperature and I know what the Celsius temperature is, I simply have to add 273 degrees. So for example, the freezing point of water is 0 degrees Celsius, and I would add 273 to that, and that would tell me that it's 273 Kelvin. It's 273.15, but we're just going to use 273. The boiling point of water is 100 degrees Celsius. If I add 273 to that, I get 373 Kelvin. And then room temperature is around 22 degrees Celsius. And if I add 273, I get 295. So I can always figure out, if I know the Celsius temperature, I can figure out the Kelvin temperature by just adding 273. And those divisions on the scale are exactly the same. So if I put my Kelvin scale right next to my Celsius scale and I drew divisions on my thermometer, they would each be the same separation distance on there. You'll notice that there's a picture on the right, and that just gives us some idea of some different temperatures and also, you know, what's going on at those temperatures. So, you know, down here we have, you know, dry ice vaporizes at around here, negative 100 degrees. It's probably a little higher, like negative 80 something degrees Celsius. Over here we have 0 degrees Celsius, which is 273 Kelvin. That's when ice melts. We have water boils, so at 100 degrees Celsius, somewhere right here, and so on. And then we can get all the way up to really, really high temperatures in Kelvin, right? So this is 100 million Kelvin for a hydrogen bomb. The center of the sun is 20 million Kelvin. So, and you'll notice there's no cap here, right? So there's no cap on how high the temperature can be. But there is a cap down here, right? 0 Kelvin. So when we're doing any sort of calculations that are involving temperature, Kelvin is the standard unit of temperature, and it's directly proportional to the internal energy. So if we needed to measure something related to the energy of a system, we will always use the temperature scale of Kelvin. It's the more scientific scale. Celsius is sometimes used, but Fahrenheit is never used in calculations. Now, Fahrenheit in the US is what we use when we measure the temperature outside. So when it's 80 degrees outside, it's 80 degrees Fahrenheit, not Celsius. So keep that in mind that we have to use Celsius in any type of scientific calculation that we're using here in physics, and specifically. We'll use Celsius or Fahrenheit when we're working with temperature differences. So it's okay to use Celsius if we're talking about something that is related to the temperature difference. If we want to know a very specific temperature for a calculation, it's related to its energy, then we have to use the Kelvin scale. We will never use Fahrenheit in physics. I wanted to just sort of point out these temperature scales again, and I wanted to show that it's kind of hard to see on here, but the divisions on, if I have a Kelvin scale and I have a Celsius scale, the divisions are actually the same size. So like if I go to the top, right here is 90, and then I go to 100, there should be 10 divisions between 100 and 90. If I go to the other side for Kelvin, 100 degrees Celsius is 373.15 Kelvin. And if you go down to where the 90 is, it's 263.15 Kelvin. The difference between 273 and 373 and 363 is another division of 10, right? So all of these divisions are equally spaced for Kelvin and Celsius. So if I said the difference between 0 and 100 degrees Celsius, it's 100 degrees. The difference on Kelvin for that same range is also 100 Kelvin, right? 273, 373, the difference is 100 Kelvin. That's not true on Fahrenheit. So the difference between 0 and 100 is 100 degrees Celsius. Over here, the difference at that mark on the 0 is the difference between 212 and 32 is 180. So the divisions over on the Fahrenheit scale are smaller because there's a bigger gap, 180 versus 100. So pretty much just ignore Fahrenheit. We're not going to use it. We'll use Kelvin for specific measurements, and we'll use Celsius if we're talking about temperature differences. So our internal energy is going to be, as we talked about, it's equal to the total energy of the substance, which is summing up the kinetic and the potential energies. And it's going to be directly proportional to the temperature in the Kelvin scale. So again, 0 Kelvin means 0 kinetic energy. And as the temperature in Kelvin goes up, the kinetic energy, the average kinetic energy of the molecules that make up the substance increases. And the internal energy also is directly proportional to the number of molecules that make up the material. So if you have more of a substance, even if it's at the same temperature as another, as less of that substance, it's going to have more internal energy. So just as a sort of a last final talking about the difference between temperature and thermal energy, temperature is related to the average kinetic energy of the molecules. So I have two different containers here. They look like they have water in them. Obviously, the one on the left has less water. The one on the right has more. So even though they're both at 100 degrees Celsius, they have the same temperature. So if I looked at the average kinetic energy of the molecules on the left, it would be the same average kinetic energy as the molecules on the right, because average means we sum up all the kinetic energies and then we divide by how many of them we have. Even though we have more of them here, we're taking an average. So same temperature, but different amounts of thermal energy. So the thermal energy depends on the total kinetic energy. There is, even though they have the same average kinetic energy, there is more material here on the right-hand container, and so there would be more thermal energy because there's more of the substance. And this is just another picture sort of representing the same thing. Obviously, on the picture, the block here on the left, these molecules, maybe it's a gas, have the same average kinetic energy in both of these cases. The arrows are sort of representing their velocities, and more specifically, we could just say that's directly related to their kinetic energy. So on average, the kinetic energy here is the same as the kinetic energy on the right, but there's a whole lot more molecules on the right-hand block, and so there would be more thermal energy just because there's more total kinetic energy because of there being more of them. So what does it mean if we're going to change the temperature of an object? How do we raise the temperature? In order to raise the temperature, we have to add energy to the molecules to make them move faster. If we want to lower the temperature of an object, we have to remove energy from those molecules and make them move slower. Right? So if we're talking about a gas or a liquid or even a solid, right? So we have to either add energy to make them go faster or remove energy to make them go slower. And how can we do that? How can we add or remove energy? Well, one way that we can do that, of course, is by adding energy, thermal energy, which is due to heat. So this is a very simple example, right? If we had a pot and we put it on the stove, we could have a liquid in there, maybe there's water in there, and we can raise the temperature by adding some energy by having it be in contact with something that's very hot, like a stovetop. And we're going to talk more about that in a little bit. So why is it that objects feel hot or cold to the touch? So So in the last example, right, we talked about how do we raise the temperature? We have to add or remove energy to raise or lower the temperature. So obviously there has to be an energy transfer. And so why is it when I take ice cubes out of the freezer, they feel cold to the touch, or if I left something metal out in the sun for the day and I go over and I grab it, it feels hot, right? So it turns out the reason that objects feel hot or cold is because there's transfer of energy to and from your body. So objects will feel cold to the touch because when you touch the object, thermal energy or internal energy is removed from your body because your body's at a higher temperature than the object, and the brain registers this as cold. So I grab the ice cube tray or the ice cubes out of the freezer, and the ice cube feels cold to me because my hand is at a warmer temperature than the ice cube. Thermal energy leaves my hand and goes towards the cooler temperature object, the ice cube, and my brain says, oh, you're losing energy in your hand, that object is cold. The reverse is true if you have a hot object. So when you touch an object that's hot, thermal energy or internal energy is transferred to your body because your body's at a lower temperature than the object, and the brain registers this as hot. So I grab maybe I left a spoon in the soup or something like that, and I go over and I grab the end of the spoon. That spoon feels hot on the stove, right? And it feels hot because the spoon is at a higher temperature, and so it's transferring some of its thermal energy to my hand, and my brain says, ah, you're getting energy in your hand, that object must be hot. So one of the things to get from this, hopefully, is that you realize that energy is always transferred naturally from the higher temperature object to the lower temperature object. So if you put two objects in contact with one another and those objects are at different temperatures, the higher temperature object will transfer some of its internal thermal energy to the cooler object. And that's the process that always happens. You can force things to go the other way, but you have to put energy in to force the opposite to occur. So here's an example of this and how objects can actually change temperature. So I have, you could imagine you have an ice cooler, right? You're going on a picnic and you fill your cooler up with ice, and then you take some sodas that you bought at the store that aren't cold yet, and you put them in your cooler. And so the ice is obviously at a cooler temperature. The sodas are at a warmer temperature when you put them in. So energy flows from the higher temperature can of soda to the lower temperature ice. The can's temperature, since it's giving some of its energy away to the ice. So the can's temperature will drop because it's losing thermal energy, and the ice's temperature actually will rise, and in some cases the ice can actually melt because you're putting energy in. Eventually, when you leave the cans in there long enough, and assuming that it's a really good cooler and you don't lose any energy to the environment, the process of this energy transfer stops when the temperatures are exactly equal. And that's when you reach thermal equilibrium. So if both of these reach the same temperature, then one is not higher than the other, and that process of energy transfer